made this possible, but for example, Luke is apparently outside still doing his organizing thing. Quick word about myself. I'm a PhD student by day, and then by night I occasionally do some shader compiler hacking. And that's what I'm going to talk about. Okay, so here's the plan for my talk. First of all, very quickly, what's GLSL? Probably most people know here, but just very briefly. Then I'm going to talk about the Radeon hardware, R300 to R500, from a compiler writer's point of view. Then kind of the main part will be some overview of what the compiler looks like right now and some thoughts on how we got there. There will be a part on what is missing for GLSL and how can we get there, and some final thoughts as well. Okay, so would you please all raise your hands for me for a moment? Okay, those, please just raise your hands. Okay, those of you who have worked with GLSL or the TGSI assembly, please put your hand down. Okay, so most people actually have, but there are some who haven't. Okay, but that's a nice trick, you know, to get everybody first to raise their hand. Okay, so here's a very rough overview of what the OpenGL pipeline looks like. You have vertex fetching from vertex arrays, you have transformations that are applied. Then in the latest versions you have a geometry shader which can again modify that output, but the hardware I'm going to talk about doesn't have it, so we can forget it. Then primitives are assembled and rasterized, the resulting pixels or fragments are again shaded, and it all ends up in the frame buffer eventually. And the point is that these yellow boxes are programmable. So you can, as you see on the right-hand side, there is some C-like language that you can use to modify the functionality of these yellow blocks. And what we need to do as driver writers is to get from this textual representation of some C code, well, C-like code, to fill in a structure like here, which just contains the binary machine code that the hardware understands. And this compilation step is what I'm going to talk about. And then once this is compiled, then every time we do rendering using that shader, we just use these stored binary values and send them off to the hardware. Actually, the GLSL, the first step of compilation is in Mesa entirely independent of the hardware. It generates a intermediate assembly language, which is also used for fixed function, old school OpenGL, for the ARB extensions, assembly extensions, and in the case of Gallium, if you have some other state tracker, like maybe the Xorg state tracker, which is being hacked on, then this also ends up in this assembly language form. So what we need to do is we need to take this assembly language and put it into machine code. And the thing is that we also need to do some optimization steps because each hardware is a little different, and the assembly that is generated by the compiler may not be optimal for what we need to do in the hardware. And here's just some example of what this assembly language looks like. So it's very self-explanatory. You have some instructions like move, subtract, multiply, and this is fairly standard stuff. Okay. By the way, if there are any questions, of course, feel free to interrupt me and ask me anytime. Okay, so about the hardware. I'm going to talk about R300 to R500, which are supported in Mesa by a single driver. Or actually, there is a single classic driver and there is a single Gallium driver, but okay. Here's what the marketing terms that this roughly corresponds to, in case you haven't seen it yet. And just let me say that the newer chips, like Radeon HD and onwards, are very different in terms of programmability, and I'm only going to mention it shortly at the very end. Okay, so we have a programmable vertex shader. That's the first yellow box you've seen. And the hardware there is very close to this assembly that we use intermediately, which is quite nice. Another nice thing is that there aren't many differences across the hardware versions from R300 to R500. And the differences that are there are all in terms of new features, so they're backwards compatible, which makes life easy for us. Let me give you an idea of what a PBS instruction looks like. So first of all, you have a bunch of register files here, indicated on the right-hand side, in which, well, you see it. Most of them are pretty standard, except for this strange alternative temporary register file here. this is just a second register file in which you can store temporary values, which has some different restrictions than the other temporary register file. And then instructions go basically in 3 steps. The first step is to select the up to 3 operands for the instruction that we want to use. Most of them have 2, but multiply and add has 3. We can select first which register we want to use. We can then take absolute values. We can do swizzling, which means exchanging components or replacing a component by 0 or 1. And then we can do component by its negation. And this is very nice because it's very flexible. In fact, you get the swizzle instruction that we have in the assembly, you get it for free. Then the instruction is executed, and then you have some post-processing as well. R500 is a bit more powerful here to support flow control, if else and if, particularly in a nicer way than we can do it on R300. And then things are stored, of course, in the registers. Okay. And okay, the machine code is just a bunch of bit fields, and basically each box that I've drawn here on the left-hand side corresponds to 1 bit field in this machine code. So this really corresponds to our view of what the hardware does. Okay, so from my point of view, what's good about it? I've already said the very flexible swizzle support. Most instructions that we want to implement are supported natively by this hardware, which is not the case for fragment programs, especially in older hardware, where you have to emulate instructions like sine, cosine, and so on. There are some not so nice things. The worst thing is that there are some operand restrictions. So if I go back here 1 slide, you have up to 3 operands, but you can only use 1 input register at a time. You can only use 1 constant register at a time. And if you want to use more, then you have to use some kind of spilling moves. You can also only use 2 temporaries at a time, which means that it would be nicer to have, if you have a multiply and add, it would be cool if we could put 2 of the operands into the temporary file and the other one into the alternate temporary, because then we could do it in 1 cycle instead of using a macro instruction that takes 2 cycles. But this is an optimization that we don't do yet because it's lack of manpower, basically. Also, a nice feature that this processor has is that you can, under certain limitations, you can combine a vector instruction with a scalar or a trig instruction. But the limitations are kind of nasty, and again, because of lack of manpower, I mean, nobody has had the time to really make use of that so far. The fragment processor. It's called US in the AMD documentation for some reason, I'm not entirely sure. The weirdest thing about this beast is that the arithmetic unit is split into a 3-vector part for the 3-component part, sorry, for RGB components, and 1 scalar part for the alpha component. What's a bit, well, tricky, but we got used to it, is that there are many changes, especially going to R500, in terms of how texture instructions are scheduled, in terms of additional features, flow control. But the nice thing is that the ALU, let's say, philosophy of having this RGB and A split has stayed pretty much the same, which makes it easier for us to share a lot of code. And again, I'll show you a similar picture than the one before. No, wait, there's another thing first. Texture instruction scheduling. It's an interesting problem as well. Because in R300, you don't have a sequence of texture and ALU instructions that are intermixed. Instead, you have 1 set of registers into which you can write texture instructions, 1 set of registers in which you can write arithmetic instructions. And then there are additional bit fields that tell the hardware that, okay, please execute first the first 4 texture instructions, and then please execute the first 10 arithmetic instructions, and so on. Like I tried to visualize here, you have 1 block of texture instructions, and they alternate. And the problematic thing is that you have a very limited number of blocks. On the R300, there are only 4 blocks of texture instructions and 4 blocks of arithmetic instructions that you can use. So you have to be careful to try to group texture instructions so that they run at the same time. Otherwise, you might not be able to support even rather simple shaders. I think there was one bug once about a Compass plugin that used 5 rectangle textures. And the thing is that rectangle textures need to get coordinate scaling via arithmetic instructions. And then we had arithmetic checks, and ran out of blocks. So one optimization we had to do was to move all these texture instructions together. The R500 is nicer in that respect. There you really have a normal sequence of instructions. The instruction format is unified, 5 words per instructions. It's very nice. There is some potential for optimization with doing manual synchronization between texture and arithmetic, which should be rather simple, but nobody has bothered so far. Yeah?
Is it still a performance improvement if you group the textures even on the R500, or does that matter anymore?
That's an interesting question, and I suspect that it does matter because you have you have a synchronization flag in the arithmetic instructions, which tells the processor, please wait until all the texture instructions are finished. So if you can do some clever grouping and maybe move the arithmetic instructions that need to use the texture result as far down as possible, then you could have maybe better throughput. So yeah, it's a good point. It still somehow matters probably, but we haven't done it. Okay, now here's what the instructions look like. The most important message is that you have this big vertical split between a 3-component vector part over here and a scalar part over there. Even the register files are, you can think of them as completely separate. And similar as before, well, this time you only have a constant and a pixel stack register file because the pixel stack contains both the temporary variables and is also initialized by the input, so that's a minor difference. You have slightly more flexibility how you control your sources and operands. So what you first do is you select source fields where registers are loaded, and then you have the ability to do swizzling across all the units, which allows, in theory, for some nice hacks, because you could have an operand here that uses the R component of register 0 and the alpha component of register 10, in theory. But I don't know if that's particularly useful. And you can do the usual modifications. Then you have the instructions, which are in principle separate, except that some stuff like dot product needs some crosslink. Also, you have the ability to take the output of the scalar instruction and replicate it over there. If you want to do that, that means you can't use the RGB instruction slot for that instruction. And, well, usual output modifications, and then you can write it to the frame buffer, or not directly to the frame buffer, of course, but to the output, which is then put into blending, or you go back to the temporary register. Okay. So some challenges here is, I've mentioned this briefly before, there are many instructions that need to be emulated, but this is relatively simple and you do that. It works well. There is this split, which is a challenge in terms of instruction scheduling. We have some code that does it, and I think it does it actually fairly well, except for one problem. I've seen a lot of shaders that do something like compute the reciprocal of a scalar that is in the X register, and write the output again to the X register. The problem with that is that the RGB unit can't do reciprocals. So what we have to do is we load the X component into the alpha, and then replicate the result to the RGB, which wastes the RGB vector slot in that instruction. And there's a question of maybe we can move these components around in a clever way, but that's a more difficult subject, I guess, and we're not doing it. Again, limited manpower. On the older chips, you have to do some swizzling emulation, but that has been pretty stable for 2 years now. So, and of course there are some little bonus features that would be nice to use optimally, like what I didn't explain is this pre-sub thing. It allows you to do something like subtract source 0 from source 1 before doing the actual instruction. This allows you to do something like linear interpolation in a single instruction instead of using a multiplication and a multiplication plus addition. Would be nice to have. There are some limitations there because you're not as flexible with swizzling when you want to do that, which is the main reason why I've been lazy so far in supporting that. Okay. There's a picture about flow control. You have the issue that when all pixels want to jump in a branch instructions, then it's fine because you operate on many pixels separately. If none of them want to jump, it's also fine. If some want to jump and some don't, then you actually have to twiddle with some deactivating some pixels temporarily and use both branches in an if-else ended. But I'm not going to elaborate on that too much. The nice thing about flow control support on the R500 is it's one, very flexible, and it's very easy to map GLSL onto the hardware actually. There are some other challenges which I'm going to mention later. There are lots of possibilities for optimization there, but we can think about that later. Okay, so far for the hardware details. And now I want to give you an overview of, well, high-level overview of how the compiler works right now and how we got there. Okay, so in the beginning, we were young and needed a driver, and we didn't know too much. We had no documentation, and so what we did was just loop over all the instructions and try to convert them into machine code as well as we could. Then as we learned more about how the hardware really works and so on, we wanted to use new features. We wanted to fix bugs that caused new complexity because you have interactions between emulating an instruction and doing the swizzling emulation on the older chips, for example. There was also the issue that initially we did the R300 and R500 fragment program entirely separately, which was not a good way to live with that, so we wanted to do code sharing there. And so what ended up happening from a very high-level point of view is that often there was a decision to take a single pass in this compiler and split it into simpler multiple passes that communicate using some intermediate representation, which change over time. And I guess that's actually the main philosophical change that took me personally quite some time to embrace, is that to really embrace multiple passes. Also, since last year, when the Gallium driver started to pick up speed, there was a decision to share the compiler between the two, to try to make it as independent as possible from the other things and just share code. So I talked about multipass, there's an explosion going on. And this is what we had initially. This is roughly what we had at the end of 2008, and this is more or less what it looks like in master right now. So you see that first the single pass is kind of split up, and first we do the emulate instructions and just replace them by native instructions in the assembly format. Then there was a strangely named, not quite static single assignment and dead code elimination pass, which also took care of doing swizzle emulation. Because there's a tricky thing about swizzle emulation. The way MESA generates assembly is that you often have swizzles, if you use only two components in an instruction, you tend to get swizzles like X, Y, Y, Y. That's not a native swizzle on R300. But actually you don't need to use the third and fourth component. You can just ignore that. And so what this pass for the first time did was to analyze which components of the input operands are actually used and then mark the unused ones and take care of that in the swizzle emulation. And then there was a separate scheduling in the fragment program, scheduling these pairs of RGB and A as well as we could. And then the emit, and at that stage actually only the final emit was different between R300 and R500, all the rest was pretty much shared, except for some instruction emulation details. And then again it split to make things slightly easier. And there is even a new pass where up here we use pretty much this assembly format as intermediate representation. Down here there is a new instruction format which is modeled after what the hardware actually does. This split really is represented in form of a C structure there. Well, what are the trade-offs of single pass versus multipass? In principle, multipass can be slower because there might be some information that you have to recompute several times. However, the advantages are really overwhelming because it's easier to wrap your head around one pass that does only a single thing instead of trying to do many things at once. So it's hopefully a lot more understandable and maintainable now. It's easier to share code because if you have a single pass that does something, then maybe it applies to some other hardware as well. And the compilation time doesn't matter that much because we only compile shaders at the start of an application, usually. And of course, this slows down the start of applications and we shouldn't completely ignore it, but it may be worth it because we don't have enough people working on this thing, and having it easily maintainable is just much more important. Okay, here's an example of how we can share passes right now between fragment program compilation and vertex program compilation. Of course, the final limit can't be shared, but dead code elimination is shared. This is a pass that only is important for vertex programs, so it can't be shared. This is something that we should share, register allocation, but we don't do it right now, which is a bit sad, but we'll get there. And instruction emulation, everything that can be shared there is shared. I mean, neither is a subset of the other, so it can't be shared entirely, but whatever we can share, we do share. So that's very nice from a maintenance point. Now, I think that to understand some program, the best way to go is to try to understand the data structures. And the most important data structure here is how do we represent the programs in the intermediate steps. And that's actually a very simple representation. It's just a doubly linked list of instruction structures. And then instruction formats come in two flavors. There's the assembly style and the one that is closer to the fragment program hardware, as I've already said. We maintain a list of constants used because we need to add constants when we emulate sine and cosine. But that's it. About this intermediate representation, I really personally like the doubly linked list because it's very easy to insert, modify, remove instructions, which is something that we do a lot. It's also easily understandable, I think. I really don't like TGSI for this kind of stuff. There is one downside, which is that to really do optimization, like peephole or whatever, we want to look at an instruction, say, okay, this instruction writes some value. Now we want to know which other instructions use this written value. And this is a query that with this representation, in the worst case, has to look at the entire program, which is slow, unfortunately. I did experiment a little with trying to do a bit more clever data structures here, which can yield an asymptotic speedup, which would be very nice. The problem is that to make sure that all the invariants that you want to have, that they are maintained, is tricky and can easily lead to bugs. Because, well, I mean, in theory, you can do all the abstractions you want in C, right? But somehow it's not very nice to express them. This is something where C++ tempts me, because there you can express some abstractions more easily. Yeah?
So when you go through a pass, modifies in place or makes a new little weights?
It modifies in place.
Oh, okay. To keep the invariants.
Yes, that's the problem there. Yeah, there are several different approaches you could try to fix it, but that's what happens right now anyway.
What about using a typical SSA in not modifying in place?
I thought about this. The kind of problem is that you often have instructions that don't, I mean, your registers are vectors, right? And they don't actually, there are many instructions that don't actually replace the whole vector, but they kind of mix the original value with some new component that gets overwritten. And I didn't really find a good way to deal with it. I don't know if there's some literature on this kind of stuff, but... I did look at LLVM. It didn't seem like it was really, I mean, it was rather geared towards what you have in a usual CPU, so it seemed rather problematic. Although for some of the newer GPUs, it might be worth looking at it again.
I'm not sure if there is a real drawback. I mean, we were talking about SSA representation and stuff like that. Don't go against the fact that we can use substructures of registers, basically. When you implement, I mean, even on more classical CPUs that are not GPUs, you have that problem.
Well, I guess in SSE, like these vector extensions.
SSA representation is much more higher level than that part. So I'm not sure it will be consistent with that. But on the other hand, you will have some niceties like being able to have dominators, and the queries like the one you were talking about, like word values.
They are implicit, yeah.
You have that,
yeah.
For nothing, and so yeah.
Yeah, I don't know. Maybe we can talk about this later about how you do this kind of thing in SSA. That would be interesting. Okay, another little detail is that at some point we want to do dynamic allocation so that we don't need to think about fixed size arrays, and maintaining that is a bit painful. So what we do is we have a memory pool structure which only has an allocation function. It allocates whatever you need. At the end of compilation, everything is thrown away. It makes life much easier. Okay. Yeah, this is already kind of my overview of the compiler, and now I want to talk a little bit about what we need to do for GLSL and what are the kind of the remaining things to get really good support here. What is worth mentioning at this point explicitly is that actually most GLSL shaders today work just fine. There are some features which are missing, which is why it's a bit dodgy to claim to support GLSL. Flow control, supporting vertex programs isn't there yet. Supporting loops isn't there yet. And there are some additional instructions, I think, that we would still need to emulate. But I mean, that's a small thing. The other two things are a bit more, a bit bigger. And of course, it would be nice to have a lot of optimizations. Okay, how could we go about implementing loop support? Mapping the instructions onto the hardware machine code is actually pretty simple. The real problem is that, again, it comes down to this data flow stuff, because if you right now compile a program which has loops, then the stuff like dead code elimination just doesn't understand that if you write a register here at the end of a loop and then read from it again at the top of the loop, that there is a dependency which goes backwards. There is code to support branches, so that works fine, I think. But loops aren't supported yet, and this is the harder part because some of that code is rather subtle and you have to be careful about what you modify where. But I hope to get around to that soon. Optimizations are also an interesting problem. So here's this GLSL program that I've shown at the very beginning. And here's the assembly that the Mesa GLSL compiler produces, which has 32 instructions. If you do some very clever transformations, you can get it down to 8. A bit more realistic goal, which could still be manageable, I think, would be to go at least down to 16 or something. Here is an interesting kind of philosophical problem about how you do structure things on a high level, because yeah, it would be nice to, if the hardware-independent GLSL compiler already did some optimizations. There are some optimizations that it could just do like that. The problem is that actually, well, you don't know about the final hardware. This compiler doesn't know about the final hardware, especially in Gallium, which is a bit not nice. So we can't, well, the thing is that, for example, as far as I understand the Intel hardware, they are probably actually quite happy about this kind of stuff. But we are less happy because scalars are placed pretty much randomly, ignoring this RGBA versus alpha split. So what do? I mean, do you go into the GLSL compiler, do some optimizations which would be nice to us, but then piss off maybe some other hardware? I don't know about Nouveau, what their hardware looks like, or Intel. So right now we try to do everything in the driver, which doesn't have the original GLSL. It just has the assembly and tries to understand it as well as it can.
One question though.
Yeah.
Even if you can't do optimizations at this point, have you looked at providing more information for the hardware backend? For example, when it comes to certain components that aren't used, actually tagging them in the initial format instead of having to analyze it the second time.
I guess that would be nice, but I mean, we already do this unused component analysis, which is not very complicated.
As you said, you have the slow steps of figuring out the data dependencies and stuff like that.
Yeah.
If you can already provide you that, I mean, every driver that does optimization
will need that information. That's true. Yeah, I guess there would be value in pushing this unused marker into what Mesa does and also what TGSI does. Yeah.
Is anyone looking at that? Is anyone working on something like that? Or is
I don't think so.
I
don't think so. I don't think does anybody really have this really high level view?
What I know is that I'm working on LVM pipe project, and put everything on LVM, intermediate representation. But still, there's a lot, even the translation to there's a lot of extra stuff which could be already lifted away. But the thing is, I agree with you, TGSI itself is not good for doing this intermediate classes. But if we could have a modifiable, either doubly linked or SSA representation of TGSI, which could do some of your early classes and be shared among all the drivers and get at the end TGSI, I think that would be good and useful for everybody. I'm not sure.
That would be very nice.
But we're not doing that yet. It seems a good idea.
Yeah, that's a. I agree. Lifting some of this optimization stuff into Mesa and then maybe augmenting the TGSI representation would be a very, very useful thing. Here are just some examples of the kind of thing you can do. Something that is a bit magic maybe, but actually works in R500, is here you have something that first multiplies two scalars and then subtracts them. That's this kind of, if you go back to the GLSL, that's this CRS function here, which does a kind of, well, it's a modified dot product really. And maybe we could kind of recognize that and do some magic, which actually works in hardware on R500 to save some instructions. This, by the way, is an example of why doing some of these optimizations in the device-independent code is maybe not a good idea, because if I get code like this on the R300 fragment program, then I'll be pissed off, because then I have to worry about all this swizzling here, which is not supported on R300, but R500 can do it.
One thing, you can have device-independent code, which is not shared. It's shared optionally, like the draw module.
Yes.
You opt to use it, but any driver can use it, but it's not.
That's true. That's true. The question is, do you want to do this before the gallium state tracker produces TGSI, or and you could still share it?
Drivers will just pick and choose. I want this fast and this one.
That's true. There are some optimizations that might be easier to do before the state tracker gets its hand on it, because you might have still more information about where the code comes from the GLSL. I don't know how feasible that is. I mean, the GLSL compiler is I'm afraid of that, of the GLSL compiler. Yeah, then there is some stuff that you can do with constant folding, like here. This is the greater equal comparison from the GLSL, which has a zero constant there, and we can do that more efficiently in the R500 fragment program by using some of the flow control features that it has. How do we implement such data flow optimizations? Well, one approach that wouldn't change this intermediate representation would be to have helper functions that help you figure out where values are used and where they come from, and then add the optimization just as an additional new compiler pass that just does this one thing that you can, if you have some miscompilation, you can just disable that compiler pass and see if it helps, which is useful for debugging. And then hopefully with the helper functions in place, doing the actual optimization is not too tricky. If we have an SSA-based some representation, then I guess this would look different. But this is something that would work in the current intermediate representation model that we use. Okay, and with that, I go to the last part about code sharing, R600, and some other stuff. As far as code sharing is concerned, well, we've already seen a lot of examples that are rather hardware specific that you just cannot share. But I think there are still many things that could be shared and that would be nice if you could share them. The real problem, which I think also already appeared in the discussion, is that to be able to share code, we need to share data structures. And we have to somehow agree on something that works well there. And that's maybe for some future discussions. R600 is interesting because it has the same processor for vertex, fragment, and geometry shaders. There already is an assembler that I think works fairly well. It doesn't do any optimizations, however. The processor is quite interesting because it has 4 separate ALUs that are for the vector instructions, but you can actually do different instructions on each component. And then there is an additional 5th unit that can also support these reciprocal sine, cosine, these more esoteric instructions. I think that GLSL that uses a lot of scalars maps very well onto this model, but there are some problematic operand selection restrictions that if you really want to use the hardware tool's full potential, you have again, how do you do the instruction scheduling exactly? Do you maybe move some components from the X to the Y or somehow? Of course, we can't reuse anything that we did for the R300 because the split is just too different. But again, optimization passes would be nice to share. Okay. Now there is one slide on how to get involved in shader compilation stuff. It is a bit scary, I have to admit. Here's what you need to have before is you do need to have some understanding of GLSL and of these assembly instructions. Otherwise, there's no way to really wrap your head around this. The best way to get this, I think, is to just hack on some toy applications, or maybe if you want to have some new Compass plugin or whatever that you want to work on, that would be a nice way to learn it. You definitely don't need to be a 3D expert. You just need to understand how the GLSL works and the assembly. Of course, as for all open source projects, I mean, pick something small as a first project. Maybe something nice would be if you have some really used shader from some open source game or from Compass, and you just look at what does the compilation result look like right now. There are some debug flags that you can toggle to enable this output. Then you could look at the assembly that it generates, and maybe you notice something that doesn't look good, that could be easily optimized, and then try to optimize that. And of course, I think it's a learning by doing thing, because there's really no book on the subject, I think. I mean, there are some books on general compiler design, of course, but I don't think there's anything about shader compilers in specific. Okay, and one more thing about maybe thinking about how do we improve the way that we work. Because if you have better tools for your development, then of course you don't have to worry about the small stuff as much. One important thing is to keep the source document maintainable. I mean, everybody knows this. I'm preaching to the choir here probably. But I think the things that we did in the compiler by going to multipass and so on, they helped a lot in that respect. There is the question of maybe programming at a higher level. I know C++ is a touchy subject, but sometimes I feel like it would be nice to have. I've heard that some compilers, they use some pattern-based optimization stuff where you just, you have something like, if you have a multiply followed by add, then just combine it to one instruction, and lots of patterns like that. And maybe instead of writing specific C code for each of these replacements, maybe we could find something higher level that just describes these patterns and these transformations in some very high level language, and then do some generation that produces code to do that. There's some theory. Then when you modify something in the compiler, it's very easy to break stuff, especially some subtle Swissling combinations and so on. So it's good to have automated testing, so test, 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 right? Nice heuristic is that if there are no pidlet regressions after you change something, then probably you're fine. I mean, it's no guarantee, of course, but I think the test suite right now covers a lot of things that are typical bugs that are reintroduced again and again when you work on the compiler. Kind of crazy idea here to make the thing even more robust. Maybe we could generate shaders randomly and then just render using them and compare it to some software rasterizer output. Maybe that would be an approach that helps us find more compilation bugs. I haven't tried it, so maybe something to hack on. And I mean, if you have some ideas, of course, it's always nice to share these insights. And yeah, I think I was faster than I thought I would be, and I'm done. So thank you for your attention. That's it. So this means that there is no time for questions if there are some left.